So I'm going to present some work today that's a result of a sediment coring campaign that's been conducted for the last few years as part of JOSM, as part of the Joint Oil Sands Monitoring Program. And I can't take all the credit for this. In fact, this has really been led by Jane and Derek from Environment Canada. And Jane's here, so if you have questions, you can find her as well after the talk. So I just wanted to put this up to remind everyone, I don't think anyone needs reminding, but that there's a long history of bitumen extraction in the region, and this goes back to the late 60s. There's been changes in the rate of that extraction through time, and there's been changes in the technology used to extract bitumen through time. But what you don't see up here is a consistent, comprehensive monitoring program that has spanned that entire time period. And so as David mentioned earlier, we had the Athabasca Oil Sands Environmental Research Program back in the 70s and early 80s, and that was turned off then. There's been the Northern River Basin Study, the Northern River Ecosystem Initiative, and then the RAMP program, and now we have JOSM. And so what's lacked over this entire time period is a consistent monitoring program to assess cumulative effect over this time. And so one way we've tried to address that as part of JOSM is to use sediment cores to sort of look at the accumulation of metals and a bunch of other contaminants over this time period, and indeed even further back in the past. And I'll explain how that works in a moment. The program is predicated on this idea that there's emissions from oil sands mines and from oil sands mining activities, including the open pit mines, the upgrading, the hauling of bitumen or the transport of bitumen to the upgraders, and the tailings ponds themselves. And so I want to focus today on the heavy metals, specifically lead, mercury, and vanadium for a few reasons, which I'll go into in a moment. But we're looking at a whole suite of contaminants that are emitted as a result of these activities. And there's other published work and other work that's going to be presented a little bit later on looking at that. So I just thought I'd put this up, and I actually didn't know Bill was coming today, so this works out really well. I think this slide really captures some of the controversy around the emission and deposition of heavy metals in the environment. This is two papers. The first one is probably no stranger to anyone here. This is Aaron Kelly's work, which was published in PNAS in 2010, and a subsequent paper that's been published in the last couple of years by Bill's group out of the U of A. And two conflicting titles here, and I'm going to come back to this in the end. So what have we done under JOSM? So we targeted small lakes in the oil sands region. We've now cored about 25 of these. In the wintertime, we would take a helicopter and every day try and hit a new lake. And we've deliberately tried to target small lakes that have small watersheds. And the reason for that is that we're interested in what's being deposited from the atmosphere onto the landscape. And anytime you have a large watershed, or if you have a watershed of a lake that's been heavily disturbed by anthropogenic activities, so things like roads or pipelines, that kind of thing, that can confound the signal, the atmospheric signal that's recorded in the lake sediment. And lakes are really one of the ideal recorders of what's been deposited in the past, because at the bottom of every lake is mud, and that mud accumulates 24 hours a day, 7 days a week, 365 days a year. And as that mud accumulates, it incorporates information about what's landed on the lake and settled to the bottom, but also information about the lake itself. So information about the bugs that live in the lake, the history, the climate history of the lake, and the contaminant history of the lake. So these are the lakes we targeted as part of this work. We tried to collect sediment cores from a number of lakes located on a gradient away from the mining activities. I'm going to try and group these a little bit and talk about them in terms of averages for each of these groups. And so you can see those two blue dots there in the middle, NE20 and NE13. So these are both labeled because they're 13 and 20 kilometers from AR6, which is that star in the middle. And this was sort of designated as the center of mining activities, or the midpoint between the two upgraders, by Erin Kelly in her 2010 paper. And so I'm going to present some data later on that sort of shows this data spatially as a function of distance from AR6, but here I've grouped them according to that distance. And so the two blue dots are within 20 kilometers of AR6. The green dots are sediment cores that were collected from lakes between 20 and 50 kilometers from AR6. And the red dots are lakes that were collected greater than 50 kilometers away from AR6. And we've since done more coring than what I've shown here, but we've I'm going to present the data we have so far. And a number of these lakes, we also have lake water quality monitoring data that was generated under the RAMP program, and so that's those lakes that are indicated with RAMP at the beginning. And so we have a number of years of data that we can compare some of our sediment results to lake water chemistry. So how do we do this? We land a helicopter on the lake ice, drill through the ice, and collect 3 sediment cores from 3 very close but different locations on the lake basin. We extrude these into essentially hockey pucks at half-centimeter intervals, and so you can think of each one of those as representing the gradual accumulation of mud on the bottom of the lake over a given time period. And in these systems, I'm not going to show the results of the dating, but in these systems, each of those half-centimeter slices represents about 10 years worth of accumulation, 10 or less years. And so what we're looking at is a sort of a decadal average back through time with each of these slices. We measured a whole suite of parameters on each of these slices of mud. We looked at heavy metals by ICP-MS, but there's also been work done looking at pHs, at mercury, at chlorophyll A to look at the productivity of these systems through time. We've looked at the quantity and quality of carbon and nitrogen in these systems, looked at diatoms to look at what's living in these lakes, and starting to look at black carbon. And a lot of this is the subject of a PhD student working at Queen's University with one of our collaborators, John Small. So I want to focus on a few key elements. The first is vanadium, because it happens to be enriched in bitumen, which relates to how the bitumen formed and oil formed in general. The second is lead, and the reason for that is that there's good evidence that lead has been declining in the atmosphere as a result of the phase-out of leaded gasoline, and there's good monitoring for lead in the Canadian atmosphere since going back to the 1970s, and a number of sediment core and ice core and other core work that's been done looking at how lead emissions and deposition rates have changed through time. And finally, the third element I want to focus on today is mercury, and that's because there's concern in the region about mercury concentrations in fish. There's concern because of a paper that was published recently by Jane et al. That looked at mercury, methylmercury concentrations in snowpacks around the region and showed that there was a spatial gradient with the highest mercury being deposited closest to the mines. And so I'm going to focus on these 3 today. So I've shown a couple plots here. First, one for vanadium and one for aluminum. I've shown aluminum because it's a good tracer for weathering in watersheds in general, and it's often used as a tracer for erosion or for weathering. And so anytime you get a period of higher rainfall, perhaps in the past, then you would have an increase in aluminum being washed into these systems. And what you'll notice here, and I've grouped these, I should mention that I've grouped these according to distance. So the blue curves are the average for the near field sites, the green curves are the average for the midfield sites, and the red curves are the average for those far field sites, so those ones that are 50 kilometers or greater away. And what you'll see, and this is really evident in that red curve, those far field ones, is that there's a clear relationship between vanadium, which is what we're using as our tracer for oil sands, and aluminum in these far field systems. And so when you have peaks in the red curve, you have covariate peaks in aluminum, well, in both vanadium and aluminum. The other thing you'll notice is that there's spatial and temporal variability in both the concentration and in the flux, which is the graph I just covered up. And this variation reflects changes through time and through space in the deposition of these elements, the lakes. And the other thing you'll note is that there's a clear increase in near-field sites in vanadium that's independent of aluminum, and that's that increase in the blue curve in the most recent time period. So I don't want to focus too much on concentration and fluxes because they vary a lot between the lakes because of differences among the lakes, both among the lakes and their watersheds. And so what I've done is I've calculated 2 ratios. The first is an enrichment factor. And this is a standard way to normalize for the input of erosional material into a lake system. And so essentially what we're doing is just calculating a ratio of the trace element you're interested in this case vanadium, lead, and mercury, relative to aluminum for each of those core intervals, and then normalizing that relative to the background for each lake. So the background from each core. So that's sort of a concentration ratio, and the second one is a flux ratio. So this actually accounts for changes in sedimentation rate because the mud doesn't always accumulate at the same rate through time. And so this gives a relative increase in the rate of accumulation of that element for each site. And it's a good way to compare among different lakes. And these are two very standard techniques. They've been used in everything from peak cores from Europe to the Greenland ice core to lake sediment cores from all around the world to look at how lakes respond to changes in atmospheric emissions and deposition of heavy metals. So I'm going to show vanadium first and talk about that initially. The first thing to note here is that these enrichment factor and flux ratios do not always agree. And that's because they integrate different processes. And so you can see shortly after 1850, there's an increase in the flux of vanadium, so in the accumulation rate of vanadium in near-field sites, so we don't see any corresponding increase in the enrichment factor. And so what that's telling us is that in the late 1800s and early 1900s, there was an increase in vanadium to some of these systems, especially in these near-field systems, but that was related to an increase in weathering. It's not related to activity, it's not related to any anthropogenic impact, but instead is related to weathering. After that, we see an early increase in both the flux ratios and in enrichment factors beginning around 1960. And this is really evident in these near-field sites where in the enrichments, increase from an enrichment of 1, so no enrichment, all the way up to 12. And in the midfield sites, we see an increase of about a 3-fold increase to midfield sites, so that's within a 50-kilometer radius. The final thing to note is that there's this clear post-1980s decrease in these near-field sites. So we peak somewhere around 1980, and since that time, the enrichment factor and to a lesser degree the flux ratio have decreased through time. And so that was kind of an interesting finding, and we wondered what might have caused this recent decrease in vanadium deposition to these lake systems. And so I turned to some of the work that's been done by WBEA, the Wood Buffalo Environmental Association, and to try and understand, and their work looking at sources in the region of vanadium to try and understand what might have driven this decrease. And there's sort of two ideas that we came up with. The first is that in the 80s and the 90s, there was a phase out of the use of conveyor belts to transport bitumen from the mines to the upgraders, and instead they were replaced with these heavy haul trucks. And so one idea was that the phase out of those conveyor belts would have decreased the amount of bitumen dust that's blowing around the landscape. But the other idea is that changes to the upgraders themselves is responsible for this decrease. And so I think it was in the late 70s that these upgraders were, precipitators were installed on the upgraders, and it led to a decrease in the amount of PM and the amount of particulate matter that was emitted out of the stacks. And Matt Landis and others from the EPA and from WBA have characterized the vanadium concentration in some of the sources in this region, and what they found is that even today, the stacks themselves have some of the highest vanadium concentrations, or the particles coming out of the stacks have some of the highest vanadium concentrations of any of the sources up there. And so what we suggest is that the decrease in vanadium through time is actually due to a change in the emissions coming out of the stacks as a result of improvements to stack emissions. So sort of a good news story there. So I want to move on from vanadium and talk a little bit about lead. So similar to vanadium, we see a late 19th century and early 20th century increase in the flux ratio that we don't see in the enrichment factor. So again, that's a result of erosion or weathering in these watersheds. But we see an earlier increase in the enrichment factor and in the fluxes that we did not see in the vanadium. And this is beginning as early as 1925. And not only that, but we see about a 5-fold increase in lead deposition, at least in the enrichment factor, to both near and midfield sites. And so what we suggest is that this reflects sort of the onset of anthropogenic activities in the region in general, probably more focused on Fort McMurray, and that there was enhanced lead deposition in the region as a result of these activities that we don't see in these far field sites. But we do see a small increase in the location is located more than 50 kilometers away, and that's that line in red. And it looks like a very small increase at this scale, but there's actually about a 2-fold increase over the 20th century, which is consistent with what we see in other regions across North America. Finally, I'll move to mercury. Mercury is kind of an interesting one. We don't see any of these clear increases and decreases through time that we saw in the vanadium or in the lead. Instead, what we've observed is a secular 20th century 2- to 3-fold increase among all of the sites, regardless of where they're located, regardless of their distance from mining activities. So this is really interesting because we know from the snow work that Jane's done that there is a clear spatial gradient in mercury deposition across the landscape, but that spatial gradient does not appear in the lake sediments that we have recovered so far from this area. So in terms of lake sediments themselves, we don't see any evidence for an impact from oil sands mining or upgrading on either the enrichment or on the deposition of mercury to these systems. It's also worth emphasizing, I think, that these ratios that we see in these systems are very, very quantitatively similar to a whole network of lake sediment cores that's been collected and recently summarized in a paper this year from across North America. And so this was a USGS-led effort, 5-year effort to look at mercury in Western North America. And part of that included synthesizing all of the lake core work that's been done in that region. And similar to this, it was found that there was about a 3-fold increase in both enrichment and in flux ratio through time in those systems. So I just want to end with a quick slide about integrating archives. And what I've done here is I've obtained some of the data from Jane's snow work, some of the lichen data from Matt Landis and WBEA, and some of the moss data that's been published by Bill Shattuck back in 2014. And what I've shown here is sort of a different way to look at that data. And I've plotted distance from AR6 on the x-axis. So this is a radius moving away from AR6. And then snowpack loads on the y-axis on the left and the lichen or the moss concentration on the right. And what you'll see is that regardless of the archive you use, and all these archives have seasonal biases, they all tell essentially the same story, which is that as you move away from AR6, so as you move away from that midpoint between the upgraders, you see a decrease in the concentration or in the loading of vanadium to the landscape. And so I think there's actually quite a bit more agreement in these different archives than maybe has been appreciated in the past. So just a couple slides in conclusion. There's a clear spatial pattern of heavy metal contamination or deposition in the Athabasca oil sands region, regardless of the archive you use. There's a regional impact that extends beyond those elements that are enriched in bitumen, like vanadium, but that also includes things like lead. And there's been a change, we think, in emission sources through time from the stacks to potentially to fugitive dust, which is probably more important today.
Do you have any explanation about the lack of a trend in mercury in the sediments? Is it possible it's being exported from the catchment or accumulating in biota, which simply doesn't show up in the sediment cores?
The short answer is no. I don't have a good explanation. I think that's, that was really surprising, and I think it's definitely worthy of investigation. I think we need to understand what's happening to this mercury that's so clearly elevated in the snowpack close to the mines, but it's just not showing up in these lake sediments. Now, that's not saying that there isn't a mercury problem. It's just saying that we don't see evidence for it in these cores, or at least for enrichment.
So thanks very much, Colin. Bill Shattuck, University of Alberta. So Colin, recently in the Edmonton Journal, David Schindler was quoted as saying, Environment Canada has clear evidence of increasing atmospheric deposition of lead in lake sediment cores. Could you re-show us that lead enrichment factor diagram and comment on David Schindler's comment, only because there are people who are genuinely concerned about lead in the environment? Thank you.
So I don't know that Dave said in lake sediment cores. I think he said through time. And I think there's a sort of a mix-up in spatial scales. And I think what Dave was referring to was some of the snow data that's now been generated over the last 3-4 years. And if you look at from year to year, the snowpack lead load, that has increased over the past 4 years. But this work, and I think your work and others, has focused more on decadal. As I mentioned, each one of those intervals represents sort of a decadal average. And so we're really taking the long view here and looking at lead deposition back over decades, whereas I think Dave's comment was really focused on the last few years. That's my understanding, or my best guess, based on my reading of what Dave said.